Um, I believe we are on chapter 9. Just check here. Yeah, benzene. Okay. Download that. Whoops. Okay. Okay, good morning, everyone. Can you hear me okay?
Yep.
Okay, great. Okay, we'll start a new chapter today. And I'll start sharing my screen. Okay, we'll wait for that to load. Okay, today we're going to begin discussing benzene and its derivatives. Okay. Okay, as soon as I get that to load. There we go. Okay, benzene and its derivatives. Okay, we often write benzene as a hexagon with alternating double and single bonds. Even though we show double bonds, benzene is not an alkene. It does not react like alkene. So it's in a separate functional group. Okay, benzene is not the only aromatic compound, but we'll spend most of our time looking at benzene. The first structure for benzene was proposed by August Kekule in 1872. Okay, he suggested that benzene consisted of a hexagonal ring with alternating double and single bonds. But this did not account for the unusual reactivity of benzene. It's been said, according to the folklore, although historians have cast some doubt on this subject, but the story goes that Kekulé had been working on this problem for a long time. Benzene had a low hydrogen to carbon ratio, which would indicate perhaps double bonds, but it didn't react like alkenes. And according to the story, he'd been working on this problem for quite some time, and he fell asleep in front of the fire, and he had a dream, and he saw all these molecules in front of his face, and in the midst of it all, there was a snake that reached around and grabbed its tail in its mouth and started spinning around and around. And supposedly he got the inspiration for the structure of benzene. Okay, he incorrectly believed that these double bonds shift rapidly back and forth. There's actually a continuous delocalization of electrons all the way around the ring. These are, in fact, called Kekulé structures. Right, the concepts of hybridization of atomic orbitals and the theory of resonance, which were developed back in the 1930s, provide the first adequate description of benzene structure. The carbon skeleton is a regular hexagon. All CC bond angles and HCC bond angles are 120 degrees. Okay, they are exactly 120 degrees. The carbons are sp2 hybridized, so there is no strain whatsoever. There's no bond angle strain at all in benzene. Okay, in the orbital overlap model, we have 6 parallel 2p orbitals. Okay, remember there's a 2s and there's two 2p orbitals, and 2 of the p orbitals were used to hybridize to form sp2. So that means there's 1 p orbital that's left over. So each carbon has an unhybridized p orbital. Okay, we can see that these can continuously overlap, as shown here. So there's a torus, or a donut-shaped electron structure above and below the plane of the ring. Right, we often represent benzene as a hybrid of 2 Kekulé structures, especially when we're looking at reaction mechanisms. Okay, each Kekulé structure makes an equal contribution to the hybrid. The CC bonds are neither double bonds nor single bonds, but there's something in between. Okay, if we took one of these structures, if the double bonds were fixed in that position, we would have 3 short bonds, the double bonds, and we would have 3 long bonds. Turns out that all 6 bonds are exactly the same length, and they're halfway between that of a typical double and single bond. Resonance energy is the difference in energy between a resonance hybrid and its most stable hypothetical contributing structure, in which electrons are localized on particular atoms and in particular bonds. One way to estimate the resonance energy of benzene is to compare the heats of hydrogenation of benzene and cyclohexene. Okay, we can measure this in a calorimeter. Okay, when cyclohexene adds hydrogen in the presence of a nickel catalyst, it's an exothermic reaction. Okay, and then benzene, shown here as though it had 3 double bonds. Okay, the heat of hydrogenation, okay, should be 3 times that of the hydrogenation of cyclohexene. Okay, but it's actually minus 209. Okay, notice something else here. Okay, with cyclohexene, okay, this takes place at room temperature, okay, 1 to 2 atmospheres. Okay, this is something you could do on the laboratory bench with some thick-walled glassware, 1 to 2 atmospheres of hydrogen. Okay, notice here for benzene, we need 200 to 300 atmospheres. Okay, so this is really hard to hydrogenate. It also requires a higher temperature. Okay, so graphically, okay, so here is cyclohexene. Okay, that hydrogenation is exothermic by 120 kilojoules per mole. Okay, cyclohexatriene, theoretically, hypothetically, should be significantly higher than what it actually is. Okay, so this difference between the hypothetical and the actual is 151 kJs per mole. And so that is what we refer to as resonance energy. Okay, so benzene is unusually stable. Okay, that's the main point here. Okay, these are some other aromatic hydrocarbons and their resonance energies. Okay, we have benzene, and then 2 fused benzene rings would be naphthalene. Here is anthracene. Okay, you might have used naphthalene or anthracene in the lab in an extraction lab. Okay, and then phenanthrene. These are just a few of the polycyclic aromatic hydrocarbons. Okay, so what makes a compound aromatic? Okay, not everything that's cyclic is aromatic. Cyclohexene, cyclohexane are not aromatic. The term originated from the isolation of a number of natural products that had fragrant odors, such as vanillin, which smells like vanilla, eugenol smells like cloves, and there's a whole variety of others. There's acetophenone, smells like pistachio, cinnamaldehyde, which smells like cinnamon. Today, though, the term aromaticity, at least in organic chemistry, has nothing to do with the odor. There are some aromatic compounds that have little or no odor. There are some that have very unpleasant odors. Okay, but to be aromatic, you must have 1 2p atomic orbital on each atom of the ring. Okay, and benzene meets that requirement. To be planar or nearly planar, so that the overlap of all the 2p orbitals of the ring is continuous or nearly continuous. Okay, so let's go back a couple of slides, a few slides here. Okay, so benzene is planar. Okay, every atom in the ring has a unhybridized p orbital. There's continuous overlap. Okay, there's some other rings that are also aromatic. Okay, so there are only certain numbers of pi electrons that are allowed for a compound to be aromatic. They can be 2, 6, 10, 14, 18, and so forth. Okay, so the general formula is 2n plus 2, where n is positive, is 0 or a positive integer. Okay, benzene has 6 pi electrons. Okay, benzene meets these criteria. It is cyclic, planar, and has one 2p orbital on each atom of the ring. Has 6 pi electrons in the cyclic arrangement of its 2p orbitals. All right, there are some aromatics, as well as just some cyclic compounds that are called heterocyclics. A heterocyclic compound will have other elements besides carbon in the ring. Okay, and some of those heterocyclic compounds are aromatic. Okay, so here are a couple of examples. Okay, here we have pyridine. Okay, with pyridine, we replace one of the carbon atoms with a nitrogen. The lone pair on the nitrogen is in the plane of the ring. Nitrogen has a p orbital, which can overlap with the p orbitals on the carbon, so it is aromatic. Pyridine is definitely not aromatic in the fragrant sense. It has a horrible smell. It's like dead fish. And then this is pyrimidine, where we have 2 nitrogens that replace the carbons. Okay, so here's an orbital picture of pyridine. Okay, nitrogen has an unhybridized p orbital, and this lone pair of electrons is in an sp2 orbital, which is not part of the aromatic system. It's perpendicular to the aromatic system. Okay, but we've got 6 pi electrons, and its resonance energy is slightly less than that of benzene. All right, this is, here we have a couple of other compounds. This is furan and this is pyrrole. Let me just go ahead and draw the structures of those. Okay, furan. Pyrrole. Okay, so this is pyrrole. This one is out on pyrrole. Okay, so how do we know when to count the lone pairs of electrons in deciding whether it's aromatic? Okay, look at the picture here of furan. Okay, furan has 2 pairs of electrons, 2 pairs of non-bonding electrons on the oxygen. Okay, they are perpendicular to each other. Okay, one of them is in the plane of the ring, so we don't count that one. The other one is parallel to the p orbitals in the ring. Okay, so we've got 2, 3, 4, 5, 6. So that's a 6 pi system, so that's aromatic. It's continuously conjugated. Okay, with pyrrole, the hydrogen is in the plane of the ring, and we do count this pair of electrons. And so again, with pyrrole, we have 6 pi electrons. Furan and pyrrole behave like benzene as far as reactivity. Okay, here are some natural compounds that have heterocyclic aromatics that are fused to another ring. Okay, this one is called indole. We have a pyrrole ring fused with an aromatic benzene ring. This one is called serotonin. It's a neurotransmitter. And it has that structure. It has a hydroxyl group and an amino group. Purine is a component of 2 of the 4 bases of DNA. This is one of them, adenine. Right, so let's look at nomenclature next. Parent compound is benzene. And if there is one substituent on the benzene ring, okay, we generally don't need a number. Okay, so ethylbenzene is the same no matter where we put that ethyl group. It doesn't have to be up here at the top. Okay, notice here many common names are retained. Okay, they've been in use for decades, in some cases over a century or more. And one of those is toluene. Okay, you might have used toluene in the lab. Okay, toluene is methylbenzene. This one is styrene. Okay, we might have some more to say about styrene later, but you've probably heard of polystyrene. It's a type of plastic where we link thousands of styrenes together. And if that's melted and blown with gas, then we get styrofoam from polystyrene. Okay, this one is phenol. And in fact, phenol is the name of a compound. It's also the name of a functional group. Okay, phenols have some reactivities in common with alcohols, but other reactivities are different. Okay, this one is called aniline. Okay, you might have used 4-nitro or p-nitroaniline in the lab. Okay, aniline is aminobenzene. This is benzaldehyde. Benzaldehyde is one with a fragrant odor. It smells like almonds or maraschino cherries. Okay, here we have benzoic acid and anisole, which is methoxybenzene. Right, so starting with benzene. Benzene as a substituent is called a phenyl. Okay, it seems like it should be called a benzyl, but it's not, it's a phenyl. A benzyl is actually a benzene ring with a CH2. Phenyl group is sometimes abbreviated as PH, benzyl group BN. Okay, so here we could call butene our parent. And so this is Z, 2-phenyl, 2-butene. This one is 2-phenyl ethanol. And then this is a common name. This is benzyl chloride. Okay, benzyl chloride is distinctly different from chlorobenzene in that chlorobenzene does not have the CH2 group. Okay, when we have di-substituted benzenes, we can locate substituents by numbering or using other locators. Typically, the more recent nomenclature simply uses position numbers, but if you go to the older literature, and oftentimes commercially still in the United States, ortho, meta, and para are still used. Okay, so this is 4-bromotoluene or p-bromotoluene. P means 1,4-disubstituted. Okay, notice here that toluene is accepted in the IUPAC. And if we call toluene the parent, okay, that automatically puts the methyl group on number 1. So that's why this is 4-bromotoluene. Similar situation here. Okay, if we call aniline the parent, the amino group is automatically on number 1. So this is 3-chloroaniline. And then we have 1,3-dimethylbenzene or M-xylene. M-xylene is still very widely used commercially. This is 1-chloro-4-ethylbenzene. We alphabetize the substituents, or p-chloroethylbenzene. Okay, so this one would be a paradox. So what would that make this one? Okay, this is paradox. That's orthodox. Right, and this one would be metaphors. Okay, if there are 3 or more substituents, then we have to use numbers. Okay, if one group imparts a special name, okay, such as benzoic acid, toluene, aniline, it becomes the parent name. If no group imparts a special name, then we number to give the smallest set of numbers and list alphabetically. Okay, so here toluene imparts a special name, so that's automatically on number 1. This would be 4-chloro-2-nitrotoluene. Okay, and we want to go around this way, not around this way, because we want the lowest set of numbers. Okay, this is another case where phenol imparts a special name. So the OH is automatically on number 1. So this is 2,4,6-tribromophenol. Okay, and then here, nothing imparts a special name. So we use the lowest set of numbers. So this becomes 2-bromo-1-ethyl-4-nitrobenzene. Okay, here are some polynuclear aromatic hydrocarbons, or PAHs. These contain 2 or more fused aromatic rings. Right, naphthalene is a white, waxy solid at room temperature, and it has been used in mothballs. Okay, some of you are probably familiar with the odor of mothballs. Okay, it's I hate that smell. Okay, here is anthracene. It's light yellow solid. You might have used this in the extraction lab. Okay, phenanthrene is an isomer of anthracene. And then here we have 5 fused benzene rings. This is called benzo-A-pyrene. Benzo-A-pyrene is pretty bad stuff. Okay, it is a carcinogen, and once absorbed, the body oxidizes it, okay, to try to make it more soluble and more easily excreted. And it does so by forming an epoxide and a diol. Okay, these are polar groups, so you'd expect the compound now to be more soluble. Okay, this contains a reactive epoxide ring, which can bind to DNA. And this alters the structure and produces cancer-causing mutations. Okay, so 2 of the 4 bases of DNA have an NH2 group. Okay, what happens is the NH2 attacks the epoxide ring, forms a bond, opens up the epoxide ring, and you have this, you got this 5-ring group that's attached to one of the bases of DNA, and this interferes with the double helical structure and base pairing, and this results in mutation. Okay, so benzo-A-pyrene is a component of soot, and especially cigarette smoke. This is one of the main carcinogens in cigarette smoke. Okay, way back in the 1700s in England, there was a British physician who noticed that chimney sweeps had a higher incidence of cancer than many other occupations, and he suggested that it was something in the environment, that there was something in the soot, chimney soot, that was causing this increased incidence of cancer. Okay, later it was determined to be primarily benzo-A-pyrene, as well as some other similar structures. Benzene is unaffected by strong oxidizing agents such as chromic acid and potassium permanganate. Okay, halogen and nitro substituents, and nitro, remember, is NO2, are unaffected by these reagents as well. An alkyl group with at least 1 hydrogen on the benzylic carbon is the one next to the benzene ring, is oxidized to a carboxylic acid group. Okay, if there's more than 1 alkyl group, each one is oxidized to a carboxylic acid. Right, so here we have 1,4-dimethylbenzene or paraxylene with chromic acid or potassium permanganate. It is oxidized to 1,4-benzene dicarboxylic acid, commonly called terephthalic acid. Terephthalic acid is a very useful compound industrially. It's one of the monomers required for the synthesis of polyethylene terephthalate, or PETE. Polyethylene terephthalate is a polymer that's fabricated into Dacron polyester fibers and mylar films. Okay, mylar is, that's what they use to make these birthday balloons. Mylar is also, if you remember the audio cassettes or video cassettes, the tape material was made out of Mylar. Polyethylene terephthalate is also used to make soft drink bottles. Okay, if any of you do recycling, PETE is type 1 plastic. Right, the most characteristic reaction of aromatic compounds is substitution at a ring carbon. Okay, so here we show chlorination and nitration. Okay, notice what happens here. This is a substitution, not an addition. Right, if we had an alkene, okay, such as cyclohexene, right, we would get the dichlorocyclohexane. We would get an addition. Okay, instead, we're getting a different reaction. Okay, if you simply mix chlorine and benzene, nothing happens. But if we add iron 3 chloride, then the reaction occurs. Iron 3 chloride is a catalyst. Okay, it speeds up the reaction, lowers the activation energy, and permits the reaction to take place. Okay, without the catalyst, this reaction is prohibitively slow at room temperature. Okay, so here we have nitration, and we use a combination of concentrated nitric and sulfuric acids. And the end result is we get nitrobenzene, NO2. Water is a byproduct. All right, here are some more substitution reactions. Right, this one is called sulfonation, where we make a sulfonic acid, SO3H. Alkylation. Okay, here we can make something like toluene or ethylbenzene or some other alkyl benzene. Okay, so we use an alkyl, usually a chloride. X is usually chlorine. And this requires a catalyst such as aluminum chloride. Okay, this is what's called acylation. And the product here is an acylbenzene, which is actually a ketone. And then in both these cases, the byproduct is HCl gas. Okay, I think we'll just get started on this. Okay, this is the most common mechanism for aromatic compounds, and it is called electrophilic aromatic substitution, or EAS. All right, the reaction occurs in which an electrophile, which we'll abbreviate as E+, substitutes for an H atom on the benzene ring. Okay, so all of these reactions that we looked at in the previous two slides, these are all examples of that. And the only thing that varies is the nature of the electrophile. Sometimes the electrophile has to be generated, okay, more often than not. Okay, so this is the overall mechanism, and these reactions will follow this pattern. Okay, so we'll generate the electrophile. Okay, the benzene ring is electron rich, so it donates a pair of electrons to the electrophile. We get a resonance stabilized intermediate. Okay, the double bonds and the plus charge are moving partway around the ring. Okay, and then instead of a nucleophile attacking the plus charge, like we saw, for example, with the SN1 or the addition reactions, what happens is a base comes along and takes this hydrogen, which is occupying the same position as the electrophile. So it pulls that off, and then this pair of electrons moves back down, and that restores the benzene ring. Okay, so this is an important point. Okay, benzene ring is very stable. Okay, to disrupt the aromatic system would be energetically unfavorable. So that's why we don't have something attack the plus charge. Okay, we wanna get back that benzene ring. Okay, so here is a specific example. This is chlorination. Turns out bromination follows exactly the same mechanism, except we use Br2 and FeBr3. Okay, so we start out with chlorine gas and using ferric chloride or iron 3 chloride, which is a Lewis acid. Lewis acid is an electron pair acceptor. Right, so this accepts a pair of electrons from chlorine. Forms this bond here. Iron carries a negative charge. This chlorine carries a plus charge. All right, and then we have a somewhat unusual dissociation, and that is this bond will break heterolytically, and that gives us a Cl plus ion. Okay, Cl plus is now our electrophile. Okay, the benzene ring attacks the electrophile. Got a resonance stabilized intermediate. And then FeCl4 minus dissociates, a chloride pulls away, grabs that hydrogen. This pair of electrons then moves toward the plus charge, restoring the benzene ring. We get chlorobenzene, we get HCl gas as a byproduct, and since FeCl3 is a catalyst, we get it back. Okay, by definition, a catalyst is unchanged. Okay, we could do exactly the same thing with bromine and iron 3 bromide. It's the exact same mechanism. Okay, here is mechanism of nitration. Okay, the electrophile nitronium ion, NO2 plus, is generated in 2 steps. Okay, we mix concentrated nitric and sulfuric acids. Okay, and you've probably learned that sulfuric acid is a strong acid and so is nitric acid. But it turns out that sulfuric acid is actually a stronger acid. And so nitric acid acts as a base. It removes a proton from sulfuric acid, and we get the conjugate acid of nitric acid. Okay, water is a good leaving group. Okay, so water leaves with this pair of electrons, and that produces the nitronium ion. Okay, something else I want to show you, and that's the complete Lewis structure of this intermediate. All right, something else that's really favorable to water leaving. Okay, notice we have two plus charges right next to each other. That's very unstable. Okay, so this is very unfavorable, and so oxygen is going to push this way and push water out. Water, and we've got NO2 plus. Okay, so we've got the nitronium ion. That is our electrophile. Okay, let's go ahead and finish up that mechanism. I'm going to erase this first part. So we have benzene. So benzene will attack Okay, so we have this intermediate where one carbon has two substituents, hydrogen and the incoming electrophile. The adjacent carbon carries a plus charge. And then water acts as the base. Water is going to take this hydrogen, and that will give us nitrobenzene. All right, we will talk about the Friedel-Crafts reactions next time. Okay, it's another example of electrophilic aromatic substitution, and I will see you on Wednesday.